Hello friend, so glad you're here tonight. Get comfortable, pull the covers up, and let the day loosen its grip. There's nowhere else you need to be. Before we begin, a small request. Most of the people listening tonight aren't subscribed. If this channel has ever helped you drift off, take a moment to subscribe and tap the like button on tonight's video. Both are free, they take 2 seconds, and they help this channel more than you'd think. And you can always change your mind later. And if you feel like it, leave a comment telling me where in the world you're listening from and what time it is where you are. I love reading them. Tonight is a slow drift through the real story of Jupiter, one true thing at a time. There is nothing to do here and nothing to remember. Each one will pass like a slow cloud, some familiar, some quietly surprising, all of them real. If you fall asleep somewhere in the middle, that is exactly how this is meant to work. Settle in, let your breathing slow down, and we will begin. One more thing before we begin. I'm also a co-founder of a sleep app, built to be the most affordable one out there. No ads, ever. Just sounds and stories made to help you sleep. It may not be released yet as this video goes up, but if you're watching a little later, it might be out by now. Just search for it, it should be easy to find. It works on iPhone, Android, and everything in between. Downloading it is the best way to support this channel. Jupiter has a diameter of 86,1840 miles, 139,1820 kilometers. This means that if you were to place the Earth alongside Jupiter, Earth would only cover about 1/11 of Jupiter's diameter. The gas giant is so large because it contains more mass than all the other planets in our solar system combined. Observations from spacecraft have provided detailed images and measurements, helping scientists understand its enormous size. Its great distance from the Sun allows for a slower orbit around the star, taking about 12 Earth years to complete one full rotation. This giant planet's diameter plays a crucial role in shaping the orbits of its many moons, which follow paths influenced by Jupiter's immense gravitational pull. The sheer magnitude of this fact highlights how dwarfed our own planet is in comparison to this king of planets. Jupiter's diameter is about 10 times that of Earth, making it a truly colossal planet. This size disparity arises from Jupiter's composition, primarily composed of hydrogen and helium gas. The immense pressure deep within Jupiter causes these gases to behave differently than on Earth, leading to its expansive diameter. Observations using infrared light have revealed the depths of Jupiter's atmosphere, further illustrating how its composition contributes to its massive size. The comparison between Earth and Jupiter highlights the significant difference in their volumes. This volume disparity is due to Jupiter's low density, with its mass spread over a vast area. Telescopic observations from Earth have been instrumental in estimating Jupiter's diameter long before spacecraft visits provided more precise measurements. Jupiter has a spot of enormous dimensions and reddish or orange-brown tint that occupied observers for several months in April 1880. This mark on Jupiter's surface is so large that it can be seen from Earth with the right equipment, but we have never set foot there to measure it precisely. It was observed by astronomers who patiently watched the planet night after night, documenting its slow rotation and the movements of such features. The spot is likely a storm system, with winds causing the reddish hue from chemicals deep within Jupiter's atmosphere. These winds can reach tremendous speeds, shaping the appearance of this vast mark on the gas giant. Over time, similar spots have been observed, each one showing that Jupiter is not a static world, but rather a dynamic place where storms and currents shape its surface. This storm's persistent visibility hints at Jupiter's complex internal workings. Observations from distant Earth reveal subtle changes in its dimensions and color over time. These markings offer glimpses into the planet's turbulent atmosphere, highlighting the constant interaction of forces beneath the visible surface. The spot's longevity suggests that Jupiter's atmospheric patterns are long-lasting, perhaps influenced by the planet's rapid rotation. By tracking such features over time, scientists can infer the presence of underlying currents and pressure systems. These observations are facilitated by modern telescopes, which provide high-resolution images of Jupiter's surface from Earth. Changes in the spot's appearance may indicate shifts in Jupiter's internal dynamics, offering insights into the planet's behavior over extended periods. Jupiter is classified as a gas giant along with Saturn, Uranus, and Neptune. These planets are called gas giants because they do not have a solid surface like Earth or Mars. Instead, they are composed mostly of gases such as hydrogen and helium, which extend down to their dense cores. The term gas giant is used to distinguish them from the terrestrial planets, which are primarily made up of rock and metal. Scientists have observed that these gas giants lack a clear boundary between their atmosphere and core. This classification helps astronomers better understand the differences in planetary structures within our solar system. These gas giants have atmospheres that gradually thicken as one descends, with no distinct edge marking where the atmosphere ends and the core begins. This lack of clear boundary is understood through observations of their dense, swirling cloud bands. By studying their spectral signatures, scientists can infer the composition and structure of these massive worlds. Unlike Earth, where a solid surface exists beneath the atmosphere, these gas giants have no such demarcation. Instead, their atmospheres blend seamlessly into their interior layers. This understanding comes from detailed analyses of the planet's rotational patterns and the behavior of their winds. Observations reveal that their cloud layers extend deeply, merging with the inner regions without a definitive edge. These gas giants possess no solid ground beneath their cloud tops, with gases compressing into liquids and possibly solids at great depths. Their interiors transition gradually from gaseous to liquid states, with no abrupt changes in phase. This knowledge is derived from comparing their densities with theoretical models of planetary interiors. Gravitational measurements have also provided insights into the distribution of mass within these worlds, supporting the absence of a solid core. Jupiter has 1,000th of the mass of the Sun, but is 2.5 times the mass of all other planets in the solar system combined. As the largest planet in our system, Jupiter's sheer size contributes to this significant mass difference. This massive planet orbits around the Sun, its gravitational pull influencing the other planets and objects within its vicinity. Scientists have measured this mass using spacecraft that have ventured close to Jupiter, providing precise data on its composition and density. The comparison of Jupiter's mass to all the other planets combined underscores its dominant role in our solar neighborhood. While it might seem vast, these comparisons help put into perspective just how large Jupiter is within our cosmic family. Jupiter's mass is a result of its substantial volume, with an average density that is less than 1/4 that of Earth. This mass dominance allows Jupiter to shape the orbits of smaller planets and asteroids nearby. By studying the trajectories of these neighboring bodies, scientists can indirectly confirm Jupiter's considerable mass. Jupiter's mass exerts a significant influence on the solar system, altering the paths of nearby celestial bodies. This gravitational impact is a tangible demonstration of Jupiter's prominence. By observing these altered trajectories, scientists gain insight into the planet's heft. The precise measurements of Jupiter's mass were achieved through meticulous analysis of spacecraft data. Jupiter's mass is also evident in its ability to trap smaller bodies like moons and asteroids into orbits around itself. This massive planet can even protect other planets by deflecting comets and asteroids that might otherwise impact them. The detailed measurements of Jupiter's mass have been refined over time, with each new spacecraft mission providing more accurate data. Jupiter's diameter is 11 times that of Earth, a remarkable difference in scale. This means if you were to place Jupiter beside Earth, it would tower over our planet, dwarfing it significantly. The sheer size of Jupiter allows for a much stronger gravitational pull. At 253 times the surface gravity of Earth, objects are held more tightly by this gas giant. This stronger gravity is a result of Jupiter's immense mass and volume, making it the most massive planet in our solar system. The larger the planet, the more its gravitational influence extends, shaping the orbits of nearby moons and even affecting the trajectories of comets. Astronomers first measured Jupiter's diameter using ground-based telescopes, later refining their calculations with data from space probes that ventured closer to this colossal planet. Jupiter's diameter is so vast that it could contain over 1,000 Earths. This scale difference highlights Jupiter's massive volume, which shapes its powerful gravitational field. spacecraft have sent back detailed images and measurements, confirming the giant planet's dimensions. Jupiter's immense size also plays a crucial role in stabilizing our solar system's structure. The massive Jupiter holds sway over its surroundings, drawing objects inward with its powerful grip. Its enormous size enables it to influence neighboring celestial bodies, shaping their paths through the cosmos. The planet's diameter has been painstakingly measured using various techniques, each building upon previous discoveries. Its substantial volume underscores the planet's profound impact on the solar system. The diameter of Jupiter signifies a planetary body that encompasses more than our Earth can comprehend. Its substantial mass attracts surrounding objects with an unyielding force, dictating their movements through the solar system. Measuring this colossal gaseous sphere involves advanced techniques from both ground-based observatories and interplanetary probes. The vast difference in scale between Jupiter and Earth underscores the intricate dynamics at play within our planetary neighborhood. The largest planet in our solar system is named after Jupiter, the king of Roman gods. This name was given by ancient astronomers who observed its bright, steady light in the night sky. They saw it as a constant presence, much like the chief deity overseeing their world. Over time, this association stuck, and the planet kept its divine name. Today, we continue to call it Jupiter, a reminder of the celestial bodies that have guided humans for centuries. Its vast size and powerful storms only reinforce the majestic image that the Romans envisioned long ago. Its steady, radiant glow in the night sky signified stability and permanence to ancient observers. They understood that it moved in a predictable path, unlike other celestial bodies. This regularity helped them track time and seasons. Its distinct hue and prominence made it easily recognizable, further solidifying its association with a dominant figure. Its consistent appearance in the night sky enabled early civilizations to develop calendars and align their rituals with its movements. They observed that it would appear each evening at sunset, a reliable sight amidst the shifting stars. Its coloration, a blend of red and brown hues, was noted by many cultures, giving rise to various myths and stories surrounding this giant orb in the sky. Its regular path across the night sky offered a sense of security to those watching from below. The planet's steadfast presence in the heavens inspired trust and reliance among ancient stargazers. They came to depend on Jupiter for marking significant events and transitions throughout the year. Its prominent place in the celestial landscape made it an essential tool for early astronomical observations. Jupiter's day length is about 9 hours and 56 minutes, a swift cycle compared to Earth's. This rapid rotation causes Jupiter's atmosphere to stretch into elongated bands. The gas giant spins so fast that its equator bulges outward due to centrifugal force. Observations of Jupiter's cloud patterns help determine this quick rotation period. Scientists track the movement of these clouds using telescopes on Earth and in space. By following specific features over time, they can accurately calculate the planet's day length. The rapid spin also affects weather patterns on Jupiter, creating powerful storms like the Great Red Spot. This quick rotation creates strong wind currents that travel up to hundreds of miles per hour. The equatorial bulge is so prominent that Jupiter's diameter at its poles is actually smaller than its equatorial diameter. This rapid spin also generates a strong magnetic field around the planet. Observations over centuries have shown that this day length has remained constant, indicating that Jupiter's rotation is steady and reliable. Jupiter's quick rotation causes its poles to receive less sunlight than the equator, contributing to temperature differences across the planet. This fast spin also influences the internal structure of Jupiter, with denser materials sinking toward the core and lighter ones rising to the surface. Over time, scientists have observed that Jupiter's bands of clouds remain consistent in their movement, reinforcing the understanding of its rapid rotation period. This continuous observation allows scientists to map Jupiter's atmospheric flow. The rapid rotation also leads to the formation of complex weather systems on the planet. By studying these patterns, researchers gain insights into the dynamics of gas giants. This persistent tracking helps understand the underlying physics that drives Jupiter's atmosphere. On December 30th, 2000, the Cassini-Huygens spacecraft made its closest approach to Jupiter. As it drew near, the craft's instruments began collecting data on the planet's massive storms and powerful magnetic field. The journey was planned with precision, taking into account the vast distances of space travel. At this point, Cassini-Huygens was a mere 9.7 million kilometers from Jupiter's surface, close enough to gather detailed information, but not so close as to risk collision. This approach allowed scientists back on Earth to study Jupiter in greater detail than ever before, learning more about the gas giant's composition and atmospheric conditions. Cassini-Huygens transmitted these findings back to Earth using radio signals, enabling scientists to analyze the data in real time. By observing Jupiter's storms and magnetic field from such a proximity, researchers gained insights into the planet's internal dynamics. This close encounter provided a unique perspective on the intricate workings of Jupiter's atmosphere. Scientists also discovered that the spacecraft's trajectory had been slightly altered by Jupiter's gravity, demonstrating the influence of massive bodies on spacecraft navigation. This minor deviation, though predictable by orbital mechanics, highlighted how celestial bodies can subtly reshape planned paths. By comparing the intended and actual trajectories, scientists refined their models for future missions. The data collected during this flyby also revealed unexpected complexities in Jupiter's magnetic field, challenging previous assumptions about its behavior. Cassini-Huygens' instruments detected intricate patterns in Jupiter's magnetic field, hinting at complex interactions within its core. The slight alteration in the spacecraft's path was a direct result of Jupiter's immense gravitational pull. By analyzing the deviation, researchers could better understand the dynamics of gravity and its effects on interplanetary navigation. These findings also emphasized the importance of real-time data analysis for making adjustments during future missions. The Cassini-Huygens spacecraft came within 6.2 million miles of Jupiter, its closest approach. This distance is vast, but not exceptional in the scale of space travel. The spacecraft's trajectory was carefully calculated to use Jupiter's gravity as a slingshot, accelerating it towards Saturn. Scientists monitored Cassini-Huygens from Earth, receiving signals that took over an hour to travel through the void. Light itself takes 43 minutes to traverse this distance. The spacecraft's instruments studied Jupiter's atmosphere and moons during its brief encounter. Data from this flyby helped refine our understanding of the gas giant's complex weather systems. The gravity assist technique allows spacecraft to change their velocity and trajectory without expending precious fuel. By harnessing Jupiter's immense gravitational pull, Cassini-Huygens was able to gain speed and alter its course towards Saturn. This method of navigation relies on the precise measurement of celestial bodies' masses and orbits. Observations from previous missions helped refine these calculations, enabling the successful execution of the gravity assist maneuver. This technique has been used by many spacecraft to efficiently traverse the solar system. It is akin to a skater gaining speed by pulling in their arms, using the planet's mass as leverage. The delicate balance of velocities and trajectories is meticulously planned years in advance. A slight miscalculation could result in the spacecraft missing its target or being pulled off course. Spacecraft traveling through our solar system often rely on gravity assists from planets to adjust their paths, conserving fuel for other tasks. The force exerted by a planet's mass can significantly alter a spacecraft's velocity and direction. This strategy is essential for deep space missions where direct routes are impractical or impossible. Scientists use sophisticated mathematical models to predict the outcomes of gravity assists, ensuring the spacecraft reaches its intended target. Jupiter has a diameter of approximately 88,843,000 kilometers. This is more than 10 times the size of Earth. The immense gaseous planet's width can be visualized by considering that about 1,000 Earths could fit inside it. Astronomers determined this measurement using orbiting telescopes and spacecraft that have ventured near Jupiter. The distance across Jupiter is so vast that light, traveling at its maximum speed, would take over a minute to traverse from one side of the planet to the other. Jupiter's diameter is so immense that it could contain all the planets in our solar system with room to spare. This measurement was refined over time as technology advanced, allowing for more precise observations. The gaseous nature of Jupiter contributes significantly to its expansive size, with no solid surface present like on Earth. Additionally, its great distance from the Sun allows it to retain much of this volume, uncompressed by intense solar radiation. Jupiter's diameter is so massive that it dwarfs all other planets in our solar system. This size is due to Jupiter being primarily composed of hydrogen and helium, gases that take up more space than the solid materials found on Earth. The immense pressure within Jupiter causes it to compress, but not enough to significantly reduce its overall volume. Observations from various spacecraft have provided detailed insights into the planet's interior structure, revealing its vast and complex nature. The enormous diameter of Jupiter enables it to exert a powerful gravitational pull, shaping the orbits of nearby moons and asteroids. Its size is attributed to the lack of a solid core, allowing the planet to maintain its massive girth without collapse. The Voyager spacecraft, with its advanced imaging technology, provided crucial data for calculating Jupiter's precise diameter. Jupiter's mass is approximately 1.9 x 10^7 kilograms. This means Jupiter weighs nearly 2,000 trillion tons, more than all the other planets combined. Its immense gravity pulls in comets and asteroids, creating a vast collection of moons. Scientists calculate this by observing the orbits of these moons, noting their slight deviations caused by Jupiter's pull. The gas giant's composition contributes to its substantial weight, with hydrogen making up most of its atmosphere, compressed into a liquid under intense pressure. Over time, as data from space probes like Juno and Voyager are analysed, our understanding of Jupiter's mass deepens, helping us unravel the mysteries of this distant world. Jupiter's mass influences its moons, causing variations in their orbits that scientists meticulously track. This gravitational force also shapes Jupiter's structure, compressing gases into denser layers closer to the core. Careful analysis of spacecraft data reveals subtle changes in Jupiter's rotation, further refining our grasp of its mass. Jupiter's immense mass also causes tidal forces on its moons, stretching and squeezing them. Observations over time reveal these forces alter moon shapes and orbits. The precise measurements from flybys provide detailed insights into Jupiter's gravitational influence. Each observation adds to our knowledge of this massive planet. Each moon's path around Jupiter is slightly perturbed by its gravity, allowing scientists to calculate its mass. The pull of Jupiter on these moons has been observed for centuries, providing a long history of data. Detailed mapping of these deviations helps determine the distribution of Jupiter's internal mass. Careful study of the orbital periods and shapes reveals the subtle yet powerful influence of Jupiter's gravity. Jupiter's magnetic field is approximately 14 times stronger than Earth's. This powerful field extends far beyond the planet, creating a protective bubble around it. The field is generated by Jupiter's rapidly rotating core of liquid metal hydrogen. When Voyager 1 and other spacecraft flew past Jupiter, they detected this strong magnetic field, confirming its existence. This field causes intense auroras at Jupiter's poles, similar to the northern lights on Earth. The magnetic field also traps charged particles, forming radiation belts that can be hazardous to spacecraft. Over time, these particles create a glow, making Jupiter appear brighter in certain wavelengths of light. This strong magnetic field is one of many fascinating aspects of the giant planet. The magnetic field shapes Jupiter's environment, influencing the orbits and interactions of its many moons. Its immense size can bend space-time, a phenomenon predicted by Einstein's theory of relativity. Observations from orbiting spacecraft continue to refine our understanding of this complex system. The field's dynamic behavior is thought to be driven by the planet's fast rotation and internal heat. This magnetic field also compresses Jupiter's radiation belts, creating a flattened shape. The field's strength varies with latitude, being weakest at the equator and strongest near the poles. This variation is due to the complex dynamics of Jupiter's interior. Observations from Earth-based telescopes have complemented spacecraft data in studying these variations. The magnetic field protects Jupiter from harmful solar wind, shielding its atmosphere. This powerful field is maintained by electric currents within Jupiter's interior. Observations of the field's fluctuations offer insights into the planet's deep structure. The field's influence on Jupiter's moons and rings shapes their orbits over time. Jupiter completes one full rotation on its axis in about 9 hours and 50 minutes. This swift spin means that a day on this gas giant passes much quicker than on Earth. The swift pace is due to Jupiter's massive size, with its immense gravitational pull causing the planet to rotate faster. Observations from spacecraft have helped us measure this rapid rotation by tracking features on Jupiter's surface as they move. This swift spin creates a dynamic atmosphere, with strong winds and storms constantly churning the planet's cloudy surface. Jupiter's rapid rotation contributes to its distinctive banded appearance, with alternating zones of swirling clouds and storms. This swift spin also influences the planet's magnetic field, creating a powerful aurora at its poles. Observations from telescopes on Earth have confirmed Jupiter's quick pace, with features visibly shifting over time. The gas giant's internal heat is another factor driving this rapid rotation, as it contributes to the planet's overall energy output. The swift rotation causes Jupiter's clouds to move at high speeds, creating a fluid and ever-changing surface. This rapid motion is driven by the planet's internal heat, which also powers its intense magnetic field. The fast rotation has been directly observed through changes in Jupiter's cloud patterns over time, providing clear evidence of the swift spin. The swift spin of Jupiter shapes its weather patterns, creating persistent storms like the Great Red Spot. This quick rotation was first estimated using ground-based observations of Jupiter's moons. The planet's rapid movement causes its magnetic field to wrap around it tightly, generating powerful electromagnetic forces. This fast pace was further refined by data from spacecraft orbiting and flying by Jupiter. Juno's orbit is indeed highly elliptical, with a closest approach to Jupiter of about 4,200 kilometers and a farthest distance of about 8 million kilometers. This means that Juno's path around Jupiter is not circular, but rather an oval shape. At its nearest point, Juno is close enough to skim the top of Jupiter's clouds, while at its farthest, it is a distant speck in the cosmic night. The elliptical orbit allows Juno to study Jupiter up close and from afar, providing scientists with a wealth of data about the planet's atmosphere, magnetic field, and interior structure. This unique orbit was chosen to minimize Juno's exposure to Jupiter's intense radiation belts, which could potentially damage its instruments. By looping around Jupiter in an elongated path, Juno can spend less time in the most hazardous areas while still gathering valuable data. This elliptical trajectory ensures that Juno completes one full orbit around Jupiter every 53 days, providing regular intervals for observation and data collection. The spacecraft's path is carefully calculated to avoid direct exposure to the harsh radiation zones, preserving its functional integrity. Each pass allows Juno to dive beneath the cloud cover, revealing secrets of the gas giant that might otherwise remain hidden. This orbital strategy was refined through extensive simulations, ensuring optimal data acquisition and minimizing risks. This path ensures Juno's safety, allowing it to conduct its mission effectively. By skirting the most hazardous regions, Juno can maintain functionality over extended periods. The elongated orbit provides varied perspectives on Jupiter, enhancing scientific understanding. Careful planning and adjustments are continually made to optimize Juno's trajectory. Jupiter's equatorial diameter is about 102,800 kilometers, while its polar diameter is about 100,700 kilometers. This means that Jupiter is not a perfect sphere, but rather an oblate spheroid. The difference in diameter is due to the planet's rapid rotation on its axis. Observations from spacecraft and ground-based telescopes have provided detailed measurements of these diameters. The equatorial bulge is caused by the centrifugal force that acts outward, distorting Jupiter's shape. This phenomenon is a result of the balance between gravity pulling inward and the rotational speed pushing outward at the equator. This distortion is visible as a slight flattening at Jupiter's poles and a bulging at its equator. The rotational speed causes a decrease in gravitational pull at the equator, leading to this deformation. This observation has been made possible by advanced imaging techniques that capture detailed views of the gas giant. The study of this phenomenon contributes to our understanding of planetary dynamics. The shape of Jupiter is influenced by its swift rotation, causing a flattening of the poles and an expansion at the equator. This deformation highlights the dynamic nature of planetary bodies, continuously reshaped by their motion. Observations from various angles reveal this distortion more clearly, showing how Jupiter's form deviates from perfect spherical symmetry. The careful analysis of these visual data points further solidifies our comprehension of celestial mechanics. Jupiter's oblate shape is evident in its visible cloud bands, which appear distorted near the equator. The planet's internal structure, primarily composed of hydrogen and helium, also influences this deformation. By studying Jupiter's gravitational field variations, scientists can determine the distribution of mass within the planet. Additionally, the oblate spheroid shape of Jupiter is a common characteristic among rapidly rotating planets in our solar system. Jupiter was discovered in 3003 by Arabian astronomers. This was long before the advent of modern telescopes, relying instead on keen eyes and meticulous record-keeping. The ancient observers noted Jupiter's steady movement among the stars, distinguishing it from the wandering planets we know today. Over time, they tracked its path across the night sky, revealing patterns that hinted at a larger orbit around our Sun. Their observations laid the groundwork for future astronomers to understand the gas giant's role in our solar system. The steady pace and regularity of Jupiter's movement indicated a predictable pattern in its journey. These ancient astronomers observed the planet's eastward motion against the fixed stars, charting its slow progress over many nights. They also recorded Jupiter's brightness, noting how it shone consistently, distinguishing it from other celestial bodies. By carefully comparing their observations with known star positions, they confirmed that this object was indeed moving in a loop, returning to its original place after some time. These methodical observations revealed Jupiter's orbit, a path that takes nearly 12 Earth years to complete. Through patient monitoring, they witnessed the planet slowly shift positions relative to distant stars. This careful tracking helped them understand Jupiter's retrograde motion, an illusion caused by Earth overtaking Jupiter in its shorter orbit. By systematically comparing these movements, ancient astronomers began to perceive the intricate interplay of celestial bodies. Ancient astronomers deduced Jupiter's orbit by noting its recurring positions. Their detailed records revealed a pattern over years, not days or months. This cycle indicated Jupiter's distance from the Sun, far greater than Earth's. By observing these changes, they inferred Jupiter's slow revolution around the Sun. NASA's Juno spacecraft discovered a great blue spot on Jupiter. This spot is a large storm system, similar to the Great Red Spot but blue in color due to different chemical compositions at varying altitudes. The spot was identified by analyzing images taken from close proximity to the planet. It shows us that Jupiter's atmosphere is complex and dynamic, with various storms and patterns visible through careful observation. The blue hue of this particular spot indicates unique atmospheric conditions that scientists continue to study. Juno's instruments, designed to probe beneath Jupiter's cloud tops, revealed details about the spot's structure and behavior. These findings contribute to our understanding of how giant storms form and evolve in Jupiter's atmosphere. This discovery highlights the importance of color variations in observing Jupiter's atmosphere. The blue hue suggests different gases and temperatures at play. By studying this spot, scientists hope to unravel more secrets of Jupiter's weather systems. This blue storm system provides insight into Jupiter's deep atmospheric layers, as colors indicate different chemical compositions. Juno's advanced sensors detected these nuances by measuring light reflected from the spot. Observing color changes over time can reveal shifts in Jupiter's weather patterns. The blue color, unlike the red hue typically associated with Jupiter's storms, hints at variations in altitude and composition within Jupiter's atmosphere. Juno spectrometers were crucial in discerning these subtle differences by analyzing the light scattered from the spot. Observing such color anomalies helps scientists map out the intricate layers of Jupiter's atmosphere, offering a glimpse into its internal workings. Europa completes one orbit around Jupiter every 3.5 Earth days. This means that while you experience a full day and night cycle, Europa whips around its parent planet more than twice as fast. The contrast arises because Jupiter is a light gas giant, lacking the dense core of our rocky world. Consequently, it exerts a stronger gravitational pull on nearby moons like Europa. Scientists first observed this rapid orbit using early telescopes, noticing the regular movement in the night sky. Over time, these observations helped establish Jupiter's influence over its many satellites. This rapid orbit also causes Europa's days to be significantly shorter than Earth's, with each day lasting only about 3.5 hours. This swift movement is a result of Jupiter's massive gravitational influence, which draws its moons closer and increases their orbital speed. Early astronomers tracked these movements by comparing the positions of Europa and other moons through the night, gradually piecing together their orbits around Jupiter. The rapid orbital motion of Europa contributes to its tidal heating, causing internal activity. This faster movement means that Europan days are more frequent than Earth's days, resulting in a quicker cycle of light and darkness for any potential life forms on the Moon. The gravitational tug from Jupiter also leads to tidal forces, stretching and compressing Europa, which generates heat within its icy crust. The rapid orbit of Europa creates intense tidal forces, causing its surface to shift and deform with each revolution. These constant changes shape the Moon's landscape, forming cracks and ridges in its icy shell. The consistent observation of Europa's movement from Earth has allowed scientists to model these tidal effects accurately. This understanding is crucial for predicting the internal dynamics and potential habitability of the Moon. Jupiter takes nearly 12 Earth years to orbit the Sun. This journey is long and slow, covering a vast distance at a steady pace. The planet's great size means it needs more time to complete its path around the star. Observing Jupiter from a distance has allowed astronomers to calculate this duration over centuries. The red spot on Jupiter, visible through telescopes, acts as a marker for these measurements. As Jupiter moves, it carries this spot along with it, providing a reference point. This gradual movement is so subtle that it can only be detected by watching the planet night after night. The red spot's presence helps astronomers monitor Jupiter's rotation, which is slightly slower than its orbit. This observation technique, known as spectroscopy, involves analyzing the light reflected from Jupiter. Over time, these careful measurements have revealed the planet's deliberate pace. The subtle shifts in Jupiter's position relative to its background stars provide a reliable method for tracking its progress. The consistent pattern of this movement allows for accurate predictions of future positions. By comparing observations over extended periods, the exact length of Jupiter's orbit can be determined with precision. This meticulous process requires patience and precise instruments, reflecting the steadfast nature of astronomical study. The slow drift of Jupiter across the night sky is barely perceptible to the naked eye, necessitating the use of telescopes and careful recording. Each night's observation builds upon the last, creating a comprehensive record of Jupiter's journey. This patient tracking reveals not only the planet's orbit, but also its rotation, showcasing the interconnected nature of celestial mechanics. The persistent observation of Jupiter's movement has enabled astronomers to understand and predict its path with remarkable accuracy. The Europa Clipper is a mission to Jupiter's moon, Europa. This spacecraft, previously known as the Europa Multiple Flyby Mission, will study Europa, one of Jupiter's Galilean moons. It is designed to make multiple close flybys of this icy world, collecting valuable data each time it passes by. The mission aims to unravel the mysteries hidden beneath Europa's frozen surface. NASA has planned this endeavour to explore the possibility of life in its subsurface ocean. The spacecraft will carry instruments that can map and analyse the moon's surface and atmosphere. By getting closer than any previous mission, it seeks to reveal secrets about this enigmatic world. The journey through the harsh conditions of Jupiter's radiation belts will be challenging but necessary for this scientific quest. Over time, the information gathered by Europa Clipper could reshape our understanding of potential habitability beyond Earth. This mission is crucial as it allows scientists to study Europa's environment in great detail. Observations from previous spacecraft have hinted at the presence of a subsurface ocean, but direct measurements are needed for confirmation. The Europa Clipper will use advanced instruments to analyze this frozen world and gather data about its composition. This close-up exploration aims to provide insights into Europa's internal structure and potential habitability. To achieve this, Europa Clipper will repeatedly enter Jupiter's radiation belts, facing harsh conditions to acquire detailed data. The mission relies on a suite of advanced instruments to penetrate the Moon's thick ice shell. This exploration aims to confirm previous findings and shed light on the potential for life within Europa's ocean. Each close flyby will provide new insights into this icy world, helping scientists understand its habitability. The Voyager missions, Voyager 1 and 2, passed by Jupiter in the year 1979, providing detailed images of the planet. This journey gave us a closer look at Jupiter's surface and its surroundings. The spacecraft performed a flyby on March 5th, getting as close to the planet as possible without entering its atmosphere. During this pass, Voyager 1 discovered that Jupiter has a very thin ring system, previously unknown. This discovery highlighted the presence of small particles orbiting the giant planet. The detailed images captured by these missions have been instrumental in furthering our understanding of Jupiter and its environment. The particles in Jupiter's rings are mainly composed of dust, ice, and small rocky debris. This ring system is much fainter than Saturn's prominent rings, making it less visible to the naked eye. The presence of these tiny orbiting fragments suggests ongoing collisions between Jupiter's moons or incoming objects from space. Voyager's cameras were able to capture this delicate structure by using long exposure times and careful adjustments to minimize the glare from Jupiter's bright surface. The presence of these particles indicates that Jupiter's gravity continually shapes its environment. They are likely remnants from earlier collisions among Jupiter's numerous moons, with some material possibly originating from comets or asteroids. The discovery of this ring system was made possible by careful analysis of the images taken during Voyager's flyby, revealing subtle differences in brightness that hinted at the existence of rings. The existence of these rings also indicates that Jupiter's powerful gravity pulls in material from its surroundings. This continuous process shapes and maintains the ring system over time. The delicate nature of Jupiter's rings makes them difficult to detect, requiring advanced imaging techniques to observe their subtle features. Over years of study, scientists have refined these methods to better discern the intricate structures within Jupiter's environment. NASA's James Webb Space Telescope has observed Jupiter, providing new insights into the planet. The telescope, located far from Earth, can capture details that have remained hidden until now. Its powerful mirrors gather light that has traveled through space for tens of minutes to reach us. By studying this light, scientists gain a deeper understanding of Jupiter's atmosphere and weather patterns. The observations help unravel the mysteries of the gas giant's complex storms and colourful bands. The data collected will contribute to our knowledge of the planet's internal structure and composition. With each observation, we learn more about the dynamics of the solar system's largest planet. The telescope's advanced sensors detect subtle changes in Jupiter's light, revealing the planet's dynamic nature. By analyzing these variations, scientists can map out the intricate movements within Jupiter's atmosphere. Each observation adds another piece to the puzzle of how this giant planet behaves and evolves over time. These findings provide a clearer picture of what lies beneath Jupiter's visible surface, helping us understand its internal mechanisms. The telescope's infrared capabilities allow it to peer through Jupiter's thick clouds, revealing the planet's hidden structures. These observations help scientists track changes over time, providing a timeline of Jupiter's evolution. By comparing current data with past observations, researchers can identify trends and patterns that were previously obscured. This ongoing study enhances our holistic understanding of Jupiter's multifaceted environment. The telescope's ability to detect infrared light enables it to see through Jupiter's dense atmosphere, unveiling structures that visible light cannot penetrate. These observations are crucial for understanding the planet's internal processes and their influence on its exterior. By monitoring changes over extended periods, scientists can discern patterns and cycles that shape Jupiter's atmosphere. This methodical approach helps piece together the complex story of Jupiter's evolution and behavior. Juno completed its primary mission on July 4, 2021, but continues to collect data during its extended mission. This means that after a set period of time and objectives, the spacecraft keeps observing Jupiter's intricate details, extending the original goals. The mission is focused on understanding Jupiter's composition, which includes learning about the gases that make up its massive atmosphere. Juno also studies the planet's gravity field, which influences how objects move around it, and its magnetic field, a crucial aspect of its polar magnetosphere. These fields shape Jupiter's unique environment in space, offering insights into how giant planets like Jupiter interact with their surroundings. As Juno orbits Jupiter, its instruments gather detailed measurements of the planet's atmosphere, gravity, and magnetic field. These observations help scientists construct a comprehensive picture of Jupiter's internal structure and dynamics. By studying the interactions between Jupiter's fields and its environment, researchers can uncover the secrets behind the planet's formation and evolution. This extended mission allows for continuous data collection, enhancing our understanding of giant gas planets in our solar system. Juno's extended mission enables long-term observation, allowing scientists to track changes over time. This persistent data collection reveals patterns and behaviors that shorter missions might miss. By remaining in orbit, Juno can detect subtle variations in Jupiter's fields and atmosphere, providing deeper insights into the planet's complex nature. Juno's extended mission allows for gradual accumulation of data, providing a foundation for future comparisons and discoveries. The persistent orbit enables Juno to witness Jupiter's continuous evolution, revealing the dynamic nature of its environment. Through long-term observation, subtle changes in Jupiter's fields and atmosphere can be detected, unveiling deeper insights into the planet's internal processes. The Cassini spacecraft, though focused on Saturn and its moons, also observed Jupiter in 2000 during a flyby. This mission, designed primarily to study the outer solar system, provided additional insights into the gas giant's environment. As Cassini approached Jupiter, it captured images of the planet's intricate ring system and its many moons. These observations were possible due to the spacecraft's advanced instrumentation, which allowed for detailed analysis from a distance. The data collected has since helped scientists better understand the dynamics of Jupiter's rings and the behavior of its satellites. This flyby was a brief encounter, but it offered valuable information about the solar system's largest planet. The flyby revealed that Jupiter's rings, once thought to be smooth and featureless, have a complex structure with variations in brightness and thickness. This mission also highlighted the constant interaction between the planet and its moons, with some satellites influencing each other's orbits. The spacecraft's cameras and spectrometers provided high-resolution images and spectral data, enabling scientists to study the composition and behavior of Jupiter's rings and moons in greater detail than ever before. The intricate patterns in Jupiter's rings, revealed by Cassini, suggest that dust and small particles are continually reshaped by the gravitational forces of nearby moons. These observations indicate that Jupiter's environment is dynamic, with interactions between the planet and its satellites playing a crucial role in shaping the ring structure. The high-resolution data collected during the flyby offered detailed insights into how these processes unfold over time. The spectral analysis also provided clues about the composition of the ring material, furthering our understanding of Jupiter's complex ecosystem. The Galilean moons are Ganymede, Callisto, Io, and Europa. They orbit Jupiter, the largest planet in our solar system. Galilei first saw them through his telescope in 1610, changing our understanding of the universe forever. These moons are not mere specks of light, they are massive bodies with distinct surfaces and compositions. The discovery of these moons demonstrated that not everything revolves around Earth. They were named after Galileo's patron, the Medici Duke Cosimo II, whose mistresses were called Io, Europa, Ganymede, and Callisto. This naming reflects a time when astronomy and courtly love intertwined, creating an enduring legacy in the night sky. These moons, with their individual features and compositions, challenge the notion of Earth-centricity. Observations of these bodies in motion around Jupiter reveal a complex system, not a simple one revolving around a single point. Their existence prompts us to consider that other celestial bodies may also harbour their own moons. Understanding this interplay has been instrumental in reshaping our cosmological perspective. Their orbits around Jupiter reveal a complex gravitational ballet, with each moon influencing the others. This observation challenges the long-held belief that all celestial bodies revolve around Earth. Through detailed analysis of their movements, astronomers have learned about the forces at play in our solar system. The existence of these moons hints at the possibility of similar systems around other planets. These observations also suggest that moons can be distinct worlds with their own characteristics, not just reflections of their host planets. By studying their interactions and movements, scientists gain insights into the larger dynamics of planetary systems. This understanding has opened up possibilities for further exploration and discovery in our cosmic neighborhood. The existence of these moons serves as a reminder that space is filled with intricate relationships, each contributing to the overall harmony of the universe. Jupiter has 4 inner moons: Metis, Adrastea, Amalthea, Thebe, whose orbits are very close to the planet. Their paths bring them within Jupiter's vast magnetic field, influencing its complex dynamics. It was only recently that 2 of these moons, Thebe and Metis, were discovered, hidden in the glow of their mighty neighbour. These discoveries came from observing slight perturbations in the orbits of other known moons, revealing the presence of these unseen companions. Their close proximity to Jupiter means they experience intense radiation and gravitational forces, shaping their surfaces over time. The proximity also suggests that these moons may have formed from the same material as Jupiter, offering insight into the planet's early history. These tiny moons help scientists better understand Jupiter's magnetic field, as their orbits reveal subtle changes in its structure. By studying these influences, researchers can gain insights into the complex dynamics of giant planets. The discovery of Metis and Thebe highlights the significance of observing slight variations in known moon paths for uncovering hidden celestial bodies. The subtle wobbles in known moon paths are like whispers from the cosmos, hinting at unseen presences. These tiny deviations, though minuscule, can point to significant discoveries. By meticulously tracking these slight variations, astronomers can peel back layers of the universe's secrets, one revelation at a time. These subtle variations in orbital paths can be traced using advanced telescopes and computational models. Observations over time reveal shifts that are too small to detect with a single glance. The careful analysis of these shifts allows for the calculation of hidden masses. By understanding these mass distributions, scientists can infer the existence of unseen moons and other celestial bodies. The Galileo mission ended when the spacecraft plunged into Jupiter's atmosphere on September 23, 2003. This end was a deliberate choice, aiming to ensure that any potential biological contamination from Earth did not reach Jupiter's moons. The spacecraft had been exploring the giant planet since 1995, its magnetometer experiment providing valuable data on Jupiter's complex magnetic environment. Before its final descent, Galileo discovered that Jupiter's rings are surprisingly thin, with a thickness of about 30 kilometers. This thinness means the rings appear more like delicate sheets than solid structures. The spacecraft's journey concluded after nearly 8 years in orbit around Jupiter, contributing significantly to our understanding of this gas giant and its intricate magnetic field. The thinness of Jupiter's rings indicates that they are relatively young, likely formed from debris ejected by meteor impacts on the inner moons. This structure is maintained by the planet's strong gravity, which keeps the ring particles in place and prevents them from spreading outward. The spacecraft observed the rings at various angles, allowing scientists to deduce their thickness with precision. These findings have helped refine models of how planets form and evolve. The rings' youthful state suggests they are still dynamic, with a constant influx of new debris. Gravitational forces from Jupiter and its moons likely shape these rings over time. Detailed images and spectral analysis were used to study the ring particles' composition and distribution. Further exploration could unveil more secrets about this delicate system. The Galileo mission's detailed observations have offered insights into how debris ejected from Jupiter's moons forms and sustains these delicate rings. This process, driven by meteor impacts, is a continuous one, ensuring the rings remain dynamic over time. The spacecraft's data has also revealed the intricate interplay between gravity and ring particle behavior, helping to understand how they are maintained within such a thin structure. By examining the composition of these particles, scientists can trace their origins back to the inner moons, further illustrating the complex nature of Jupiter's ring system. Juno has completed over 30 orbits around Jupiter since its arrival in 2016. These laps provide a steady gaze at the gas giant, capturing details of its surface and atmosphere. Each orbit takes about 2 weeks, allowing Juno to study both Jupiter and its moons. The mission focuses not just on Jupiter, but also on its many satellites, considering them half the story of this solar system's king. By closely examining these orbits, scientists learn more about the complex interactions between Jupiter and its surrounding environment. Juno's repeated orbits allow scientists to gather comprehensive data over time, revealing changes and patterns that a single pass could not detect. By circling Jupiter, Juno can observe different aspects of the planet at varying angles and distances, providing a multifaceted view of its dynamics. This ongoing observation helps in identifying recurring phenomena and understanding their causes within Jupiter's complex environment. The data collected from these continuous laps around the gas giant enhances our understanding of its intricate interactions with its moons and the broader solar system. Juno's orbital path allows it to measure changes in Jupiter's magnetic field, offering insights into its interior structure. The spacecraft's instruments detect variations in the planet's gravity and atmosphere, revealing internal dynamics and composition. By revisiting specific points around Jupiter, Juno can compare previous observations with current data, identifying trends and anomalies over time. This methodical approach ensures that no significant detail about Jupiter's complex environment goes unnoticed. Juno's repeated passes enable it to observe how weather patterns shift and evolve over time. The gradual accumulation of data from these orbits provides a deeper insight into the planet's internal workings. By comparing successive observations, scientists can discern subtle changes that might otherwise go unnoticed. This continuous monitoring offers a detailed picture of Jupiter's ever-changing environment. Jupiter orbits the Sun at a distance of 520 AU, which is roughly 778.5 million kilometers away from our star. This orbit places Jupiter in a position where it receives less sunlight than Earth does, but still enough for its unique weather patterns to form. The distance has been measured precisely using spacecraft and telescopes, allowing astronomers to calculate the planet's journey around the Sun. It takes Jupiter about 12 years to complete one full orbit, traveling at a speed of approximately 13 kilometers per second. This vast distance from the Sun helps maintain stable temperatures on Jupiter, preventing it from overheating despite its proximity to other celestial bodies. The reduced sunlight also contributes to Jupiter's distinctive red spot, a vast storm that has persisted for centuries. This orbital distance ensures that Jupiter remains a frigid world, with surface temperatures averaging around 160 degrees C. The planet's path is consistently tracked by observatories and probes, providing continuous data on its movement and behavior. These observations have revealed the subtle wobble in Jupiter's orbit due to the gravitational influence of other planets. This measured pace allows Jupiter to retain its vast reserves of liquid hydrogen and helium, maintaining its status as a gas giant. The steady distance also influences Jupiter's strong magnetic field, which is generated by the movement of conductive fluids within the planet. This consistent orbit has been studied using orbital mechanics principles, revealing Jupiter's predictable path through the solar system. Jupiter's distant orbit provides an environment where water vapor can freeze, creating intricate cloud formations that are unique to the planet. This far-reaching journey ensures Jupiter's day is short, completing a full rotation in less than 10 hours. Through meticulous observation and calculation, astronomers have established the predictability of Jupiter's path, ensuring its role as a celestial sentinel remains consistent over time. Jupiter's atmosphere is predominantly hydrogen and helium, unlike Earth's, which is mainly nitrogen and oxygen. This difference reflects the unique formation conditions of each planet. Hydrogen and helium are lighter gases that rise to the top of Jupiter's dense atmosphere, creating a visible banded pattern. Early spacecraft observations confirmed this composition through spectral analysis. The heavier nitrogen and oxygen on Earth are products of biological activity and atmospheric chemistry over billions of years. This contrast shows how different planets can evolve distinctly under varying conditions. The lighter elements on Jupiter also make its atmosphere less dense than Earth's, allowing for easier observation. Spectral analysis has been key in understanding this composition by revealing the unique fingerprints of each gas. Jupiter's composition is believed to be similar to the primordial solar nebula from which it formed. In contrast, Earth's nitrogen and oxygen are continually recycled through processes like photosynthesis and respiration. The atmospheric composition of Jupiter and Earth highlights the distinct environments each planet has developed. The abundance of hydrogen and helium on Jupiter points to its formation in a colder region of the solar system, while Earth's nitrogen and oxygen result from continuous biological activity. Infrared spectroscopy was crucial in determining these compositions by detecting the specific wavelengths absorbed by different gases. The prominence of hydrogen and helium in Jupiter's atmosphere indicates its formation from lighter materials. Earth, with its heavier gases, shows a later evolution influenced by biological processes. The contrast between these planets underscores the significance of initial conditions and subsequent planetary developments. Spectral data from spacecraft missions have deepened our understanding of these compositional differences. All Cassini instruments except radar, radio science, and the ion-neutral mass spectrometer participated in the Jupiter flyby. This mission brought these tools close to Jupiter's surface, allowing them to observe and collect data. The flyby was a unique opportunity for these instruments to study the gas giant up close. By analyzing the data collected, scientists can learn more about Jupiter's composition and atmosphere. The spacecraft, Cassini, traveled through the solar system on its way to Saturn. During this journey, it passed by Jupiter, providing a chance to gather valuable information. The instruments that participated in the flyby included cameras, spectrometers, and magnetometers. These tools helped capture images and measurements of Jupiter's surface and environment. The data collected from the flyby continues to be studied by scientists today. The flyby was an invaluable chance to observe Jupiter's complex atmosphere, revealing its intricate layers and dynamics. The data gathered has expanded our understanding of the planet's internal structure, including its massive storms. This close encounter with Jupiter enabled the collection of high-resolution images and measurements, providing detailed insights into the gas giant's surface features and environment. By comparing these new observations with previous data, scientists can track changes over time and gain deeper insights into Jupiter's behavior. The close flyby offered an unparalleled view of Jupiter's swirling clouds and bands, shedding light on the planet's turbulent weather patterns. Observations from various wavelengths revealed hidden features and compositional details, allowing for a more comprehensive understanding of Jupiter's atmosphere. The flyby also provided crucial information about the interactions between Jupiter and its moons, enhancing our knowledge of their orbital dynamics. By studying the collected data, scientists can discern the underlying processes driving these complex interactions. The Pioneer 10 spacecraft performed the first flyby of Jupiter on December 3, 1973. This flyby was a critical milestone in our exploration of the solar system. The journey required immense thrust from its Centaur engine to reach Jupiter's massive gravitational pull. Pioneer 10 traversed the vast void between Earth and Jupiter, sending back valuable data about the gas giant. Its successful flyby paved the way for future missions, providing crucial insights into Jupiter's environment. The spacecraft, carrying advanced instruments, captured detailed images and measurements of Jupiter and its moons. As it ventured deeper into space, Pioneer 10 continued to transmit information, gradually fading as it moved farther away from the Sun. Its flyby revealed Jupiter's intense radiation belts, helping scientists understand the hazards spacecraft face. The data gathered during this encounter enhanced our understanding of the dynamics of the solar system's largest planet. Observations from Pioneer 10 provided evidence for Jupiter's Great Red Spot being a persistent storm. This flyby marked the first time humans observed another planet's complex environment up close. This flyby enabled us to witness Jupiter's auroras, similar to Earth's but more intense. It allowed us to observe the intricate interactions between Jupiter and its many moons. The data collected revealed complex weather patterns on the planet. This close encounter also helped us understand the composition of Jupiter's atmosphere in greater detail. The flyby offered a glimpse into Jupiter's turbulent atmosphere, unveiling intricate cloud formations and strong winds. Observations revealed a complex magnetic field, influencing the behavior of its moons. The spacecraft also detected signs of life-supporting elements within Jupiter's icy moon, Europa. This flyby was instrumental in understanding the dynamics of our solar system's largest planet. Jupiter possesses at least 79 known moons, with 4 particularly large ones called the Galilean moons. These bodies orbit the giant planet, tracing paths that have been observed and mapped by astronomers over centuries. Their discovery began with Galilei's use of a primitive telescope in the early 1600s, revealing these celestial companions for the first time. The immense gravitational pull of Jupiter keeps these moons in their steady orbits, each one following a path illuminated by the planet's reflected light. Their surfaces remain largely unknown, hidden from our direct view, but hinting at varied landscapes shaped by countless impacts and geological processes. As they traverse their paths, these moons cast shadows on Jupiter, briefly altering its appearance in ways that are subtle yet significant. These moons serve as natural satellites, their orbits governed by the same laws that govern our own moon. Their reflective surfaces create a dynamic interplay with Jupiter's light, casting ever-changing patterns on its surface. Observations from Earth and spacecraft have allowed us to map these intricate paths with precision. The interaction between Jupiter and its moons offers insights into the gravitational forces that shape our solar system. Their gravitational influences also affect one another, creating slight variations in their orbits. The paths these moons follow are not perfectly circular, but rather elliptical. These orbital patterns had been observed and calculated using advanced mathematical models. Over time, the moon's position shifts subtly due to these interactions, revealing complex gravitational relationships. The slight wobble in their trajectories is due to the ever-present tug of each moon on its neighbours, a delicate balance that maintains their collective harmony. This intricate choreography is meticulously tracked by observatories, using data from both ground and space-based telescopes. The subtle variations in their orbits have been meticulously measured over time, providing insights into the invisible forces at play. Each observation adds a piece to the puzzle of understanding the complex dynamics within this miniature solar system. A photo of Jupiter taken by Hubble in 2009 captures the planet's distinctive bands and storms. The image reveals Jupiter's colourful stripes moving in opposite directions. These are not mere decorations, they are currents of gas swirling in the planet's atmosphere. The Great Red Spot, a persistent storm larger than Earth, can be seen within these bands. Hubble's powerful lens allows us to observe details on Jupiter's surface from millions of miles away. Light reflected off Jupiter takes about 43 minutes to reach our telescopes here on Earth. This journey gives us a glimpse into the ever-changing dynamics of this gas giant far beyond our reach. The colourful bands are driven by winds that can reach speeds over 200 miles per hour. These powerful currents shape Jupiter's atmosphere, creating visible patterns from space. Spectroscopic analysis of the reflected light helps scientists study the composition and movement of these gas currents. Ongoing observations provide insights into Jupiter's internal dynamics and weather patterns. The contrast between light and dark bands on Jupiter indicates differences in atmospheric composition. These variations are caused by the movement of gases, with lighter elements rising and heavier ones sinking. Observing these bands over time reveals their slow evolution. Changes in color and position provide evidence for the ongoing processes within Jupiter's deep atmosphere. These bands on Jupiter are like the stripes on a tiger, each one distinct and unique. They shift gradually over time, much like the sands of an hourglass. Scientists can learn about these movements by tracking changes in light reflection. Each color we see represents different gases high up in Jupiter's atmosphere. David Shatsky became president of Jupiter-Kagan Inc. after the sale, taking on a new role within the company. This change in leadership marked a shift in responsibilities, with Shatsky overseeing the operations and strategic direction of Jupiter-Kagan Inc. Post-sale, the company's structure evolved as Tim Baskerville also took on a significant role, becoming CEO. The decision to appoint new leaders indicates a desire for fresh perspectives and expertise within the organization. This information is derived from public records and internal communications, providing insight into the company's governance. Understanding these transitions helps us see how leadership roles can change over time in response to corporate developments. The choice to bring in new leaders reflects a desire to adapt and grow with changing circumstances. By restructuring leadership, the company aims to stay current and relevant in its industry. This information comes from official documents that outline the changes in roles within the organization. Transitions like these are common as businesses evolve and face new challenges. This change in leadership is a sign that the company is looking to evolve and face future challenges. By bringing in new leaders, Jupiter-Kagan Inc. can adapt its strategies to changing market conditions. This information was learned through careful examination of official documents outlining the company's structure. Such transitions are often necessary for businesses aiming to stay competitive and relevant. Changes in leadership often signal a company's willingness to embrace change and innovation. The addition of new leaders can bring fresh ideas and approaches, enabling the organization to stay agile. These shifts are typically informed by internal assessments and strategic planning sessions. Transitions like these are part of an ongoing process of corporate self-evaluation and adaptation. And that is where we will leave Jupiter for tonight. The facts will still be true tomorrow, and this video will still be here whenever you need it. Sleep well.